Alright, so this talk titled Low Frequency Learning and Fast Adaptation in Model Reference Adaptive Control for Safety Critical Systems. And I will do an overview of what we discussed this morning. And basically, we saw those oscillations in adaptive control. This is the state response, and this is the control surface due to high gain. So I am going to present a technique developed pretty recently, actually, which gets rid of the oscillations we have in the adaptive control such that you can still achieve a same behavior but without those oscillations using low frequency learning method. So let's back up a little bit. We have dynamical systems. We do modeling by resorting to assumptions, first principles of physics and idealized assumptions. And we have mathematical models that do not adequately capture the physical system. So the objective of adaptive control design is to achieve stability and performance and maintain that performance under unforeseen and adverse conditions. We talk about fixed gain, robust controllers. Basically, if you consider this figure, if you would like to minimize a performance error, you need to know the model more. Basically, there is a direct performance uncertainty trade-off, and it can fail if you have high levels of system uncertainty. And they are tuned to the worst case that you think you know other than the physical system, assuming like the feature will be more like present, ignoring environmental changes, changing dynamics and structural damage. Whereas adaptive control, you can achieve a better performance without knowing the model, because adaptive controller tunes itself with respect to the physical system, and it does not excessively rely on mathematical models, and it adapts to unforeseen and adverse conditions. And we need adaptive control for many cutting-edge applications like high-performance aerial vehicles, space applications, underwater vehicles that their performance change with respect to density, or even with vibration separation, flow control, because flow is highly nonlinear, and even drug dosing control. For example, let's say you are going to give a desired amount of anesthesia to a patient, but that level is uncertain. Basically, it depends on patient's weight, height, and if you give less than a critical amount, patient can be awake during the surgery. So I am more interested in these 5 applications, but also there are biological applications of adaptive control that I can point you out if you are interested. So here is the design issues in adaptive control as we talk in the morning. Transient performance. If you would like to rapidly suppress the uncertainty, you need to increase adaptive control rates, which induces oscillations. And this will reduce your stability margin. So basically, high gain adaptive control, they are fragile against high frequency content, excite unmodeled dynamics, unacceptable control signals, and poor stability margins. So we need performance, but also we need robustness when we use adaptive controllers. So here is an overview of the standard adaptive control design that we discussed. We have uncertain dynamical systems, and which we parameterize the uncertainty like W transpose multiplied by sigma, W is unknown. And in this configuration, B is also uncertain. B is multiplied by D multiplied by lambda. Lambda is a positive definite matrix that is uncertain, capturing the effectiveness, uncertainty in control effectiveness. These K1 and K2 are nominal controllers, adaptive controller, and update lows. Here we have 2 update lows, because we not only interested in canceling the uncertainty due to delta, but also uncertainty in the B matrix due to lambda. So it is a slightly general version than the standard model reference adaptive control framework I presented this morning. And in this case, if you consider this Lyapunov function candidate, by using these update lows, you can prove that closed-loop system is Lyapunov stable, and error goes to 0 as t goes to infinity, and it doesn't talk about transient performance. And for the rest, for the simplicity of exposition, I am going to set lambda to identity such that there is no uncertainty in the control effectiveness, so that adaptive control signal becomes only double hat transpose beta, which we recovered the material that I presented this morning, but you can, for the method that I am going to show you next, you can simply apply it to both weight update laws. So here is the idea. We have filtering tools like L1 adaptive control, but they assumed uncertainty, a conservative upper bound on the uncertainty matrix W. And they designed, very good adaptive, robust adaptive controllers. However, here, I don't want to assume we know anything about the uncertainty. W can be anything, and we do not know an upper bound of this W simply because, let's say we know an upper bound. What happens if there is a failure to aircraft airframe during the flight? So this upper bound may be changed. So here I am not going to assume that assumption. So here I am introducing a low-pass filter for WF. So basically this is a low-pass filter provided that this is chosen to be small, such that it takes W hat, your weight estimate, as an input, and it produces W hat F, an output, basically a low-pass filtered version of the output. Because when I use high gain, in the standard adaptive control, my weights can be highly oscillative so that my control signal will be oscillative. So I don't want those oscillations. So I want my system, my weight estimation, to behave like this low-pass filter because it filters out those high-frequency oscillations. So this is a constraint enforcement problem. So we would like to minimize this cost function. You want your weight update law to behave like this low-pass filtered version. Then if you take its negative gradient with respect to this cost function at W hat, you have this modification term. So basically, to sum up, the gradient minimization yields to this new weight update law shown on the bottom of this slide. It has the standard term, and it has this modification W hat minus W hat F. Now, it looks similar to sigma modification. However, so basically, if you replace W hat F with 0, you recover sigma modification. But the problem with sigma modification is, as we discussed, if you choose that parameter to be large, then your adaptation process will be prohibited. Basically, it will drive your weight to 0 based on this cost minimization procedure. So it turns your adaptation filter to adaptation to a lag process. And that's why if you choose sigma to be large, as we discussed this morning, your uniform ultimate bond gets larger and larger. So here, I don't want to drive weights to 0. I want to drive weights to its low-pass filtered version such that I will obtain a smooth and nice and fast adaptation. Well, regarding stability, we have this closed-loop system. We have the same error dynamics. And with the modified adaptation law, you can write W tilde dynamics like this, where W tilde denotes the distance between W hat minus W, and W hat F dot is basically this low-pass filter. So regarding Lyapunov stability, if you consider this Lyapunov function candidate, you can obtain that this derivative is negative definite, and basically it shows Lyapunov stability, and if you resort to LaSalle-Yoshizave theorem, you can show that error goes to 0 asymptotically. Now, regarding performance analysis, since V dot is negative definite, not semi-negative definite, you can say that starting from these initial conditions, this V is decreasing, so that you can come up with this upper bound on the Lyapunov function initial conditions, as well as you can come up with these lower bounds on the time response of this V. Basically, you can say that transient performance bounds on error W tilde and W tilde F are upper bounded by those constants. And of course, you are more interested about your upper bound on the error. So if your initial mismatch is 0, you can see that by increasing your adaptation gain, you can make this upper bound smaller. So you need to resort to high gain. But in this framework, since you are enforcing a low frequency constraint, since you are introducing this low pass filter such that you drive your weights to its low pass filtered versions, then high gain, if you resort to high gain, then it also multiplies this sigma term, so it will enforce this constraint more and more, and it will not cause oscillations in your adaptive control response. Well, and of course you can say error and other closed-loop parameters are belong to L infinity. So here is the control architecture visualization. Now, basically these blue shaded blocks shows the adaptation. You have your standard adaptive low, but also it is feeding back. So in the actual system, your adaptive controller not only feedbacks to the uncertain dynamical system, but also there is another controller that feedbacks to the update low. The original adaptation low drives your error to 0, but this feedback shown on the bottom also drives your weight estimations high frequency content to 0, such that you can achieve a smooth adaptation. So, and for details, actually, it is recently published a few months ago, actually last December or November, in the Transactions on Automotive Control, co-authored by Wassim Haddad at Georgia Tech. So now, this selection of the filter is not unique. For example, and I am going to illustrate this in a spacecraft example in a second. So if you would like, you can include multiple low-pass filters to shape the negative slope of the filter after the cutoff frequency, such that you can more strictly get rid of those oscillations. So basically, in theory, it is possible to introduce P filters, then your Lyapunov function candidate to prove stability has this form, and you can do that, and I am going to illustrate this in an example. So for unstructured uncertainties, you can, or with time varying weights, you can also assume like there is a bounded residual error, and this time rate of change of this uncertain matrix is upper bounded by a constant, and you can resort to projection operator provided that these sigmas are scalar. Then analysis follows the same, but due to the unstructured uncertainties, in this case we don't have asymptotic stability, but we have uniform ultimate boundedness. So here is an example of disturbance rejection, because in the disturbance rejection, basis function is 1, so that we can resort to classical tools to get a more feeling of what's going on with this algorithm. So I am going to choose nominal controllers like this, and I am going to set R to identity in the Lyapunov equation, so that, as I said, we can resort to classical control tools. And here, my design objective is to achieve good tracking on this region from, I think, 10 to 20 hertz to 50 hertz. And I tuned all these controllers to achieve that suppression. Basically, this green is the standard adaptive control with adaptation gain of 100, and purple, which is not very visible here, is the other adaptive controller with adaptation gain of 10. And the proposed adaptive controller basically is the blue, achieves the same tracking objective in this prescribed region, and you can tune it if your tracking objective is in somewhere else in this body plot. And basically, it achieves the same tracking performance, but if you look at this Nyquist plot, this standard adaptive controller, in the Nyquist curve, when the adaptation is 1000, basically your time delay and gain margins are minimal. But in the proposed adaptive controller, when you increase the gain, so you have a guaranteed phase margin. Of course, it must be related to the time delay margin as well. But it has a different counterintuitive behavior. So here is the Wing-Crack dynamics example with this time nonlinear uncertainty. So here is the uncertainty where alphas, again, determined by aerodynamic coefficients of the aircraft, they are unknown. So here is the standard adaptive controller. It achieves a good tracking, but control signal is not implementable. The proposed adaptive controller achieves an almost identical response, but as proposed by the theory, this modification filters out the high frequency content in the weight update law such that your control is extremely smooth and you doesn't sacrifice from asymptotic stability. You asymptotically track the reference model as well. And here is a result that I don't have a proof yet. I have a proof with respect to unmodeled dynamics, which should appear soon. But time delay is a very special case because it makes your system infinite dimensional. And still there is a work on in this process. But I'm going to present for any case what happens when there is high gain, what happens to the margin. So here, this is the proposed design in this slide. Basically, I introduced low time delay to the actuator to make the system unstable. So here is the result. I mean, of course, when I introduce a significant amount of time delay, then my system goes to unstable, which is kind of expected. But interestingly, if you increase adaptation gain by 100 times, it recovers stability, unlike this first result. And the reason for this is that since adaptation gain is multiplied by the sigma term, it enforces this smoothness in the weight update law more and more, such that it enforces when this constraint is enforced more, then it can still recover and you can get rid of those oscillations, such that you can achieve a smoother behavior when it's compared with this example. Now, I am going to show an example on the flexible aircraft dynamics just to illustrate the either using one filter, two filter, or how many filters. So here is, we know this part of the spacecraft dynamics. This shows angular velocity, this is coupling matrix, this is control input and disturbance, and this is the model that we don't know corresponds to flexible dynamics. So, and here is the eta is the model coordinate vector, this is inertia, and this is unit quaternion for its spacecraft attitude. Well, I am going to first implement standard adaptive controller with projection operator. I need to implement with projection operator because we have unmodeled dynamics in the system, unstructured uncertainties. And then I am going to compare with low frequency learning adaptive controller, which has this form, standard adaptive control law, modified by this. Modification, this is the low pass filtered version of the weight update law. And basically, I'm going to show you the case with one filter, and then we are going to resort to multiple filters to see what's going on. And basis function here, I am going to use this basis function, and basically, I am going to design adaptive controllers without having a nominal controller, and of course, I mean, you can also have nominal controller as well. Now, here is the standard adaptation with a low gain setting, and it is highly oscillative, so I'm going to increase the learning rate, and it does a better job with moderate gain. This is the control signal, this is unmodeled dynamics, this is quaternion, and this is the angular accelerations and velocities. And basically, when I resort to high gain, it does the job, but control signal becomes highly oscillative, even though we can achieve stabilization. Now, with low frequency learning, now here I am using one filter. And actually, until I simulate, I apply this technique to this flexible dynamics, for other applications, I didn't need to use more than one filter. So here I have to use more than one filter because we have unmodeled dynamics, so that I need to shape the loop of the weight estimation such that these are not excited in the adaptive control process. So here is what's going on. This is one filter. We achieve stabilization. I mean, we have not very oscillative control signals as compared to this slide, but still we can do improvements. This is one filter. If we use two filters, we achieve this. 3 filter, 4 filter, 5 filter, and 6 filters. Basically, once you increase the number of filters, you achieve robustness with respect to those unmodeled dynamics such that your adaptation with high gain do not excite those unmodeled dynamics, because your your slope of your filter becomes more steep and steep such that you can achieve a very nice stabilization when you use 6 filters and you achieve better robustness against high-frequency dynamical system content. Basically, concluding remarks is this is a very simple technique, yet very powerful technique, which is good. And you know, we talk about adaptive controllers. We would like to achieve fast adaptation without having oscillations in the system response. And this technique basically allows fast adaptation with low frequency learning and guarantees transient and steady state performance, and ongoing research, of course, quantify, first of all, robustness against unmodeled dynamics, which should appear soon, and then time delay margins. And extensions to output feedback, I am recently collaborating with still Wassim Haddad at the Georgia Tech to do that extension based on our one of the previously introduced output feedback control schemes. If you're interested, we can discuss. Here, in this case, you don't need to know the entire state vector to design your adaptive controller, but you only need to know a set of outputs. And of course, then other technique is how to extend it to hybrid adaptive control architectures to handle, for example, sudden change in control effectiveness matrix, for example, denoting the actuator failures, so on and so forth. And I can take questions.
Stability proofs.
Yes.
Thank you very much.
Sure.
Indeed, very interesting.
Thanks.
Yeah, a couple of questions. One might be very obvious. What about problems with phase lag with all those filters in your adaptation?
I intentionally introduced phase lag. I mean, basically, when we design a nominal controller, you design your nominal controller to affect up to some certain frequency range. For example, let's say you design your nominal controller, you look at your, for example, close the body plug, then let's say you have something like this. So you want your nominal controller to be effective on this region. And because you don't want to have high gain. And basically, with adaptive control, I would like to do the same. The adaptive control, if you linearize and look at this plot, it is nonlinear. That's why I'm saying linearize. If you increase adaptation gain, it increases everything. But I don't want to have high bandwidth. I want only to cancel low frequency content of the low pass filter and achieve robustness against those contents. So basically, when designing that filter, gamma of f, I want my adaptive controller to, for example, let's say one low pass filter, to have the same cutoff frequency, but it doesn't introduce lag. Basically, if you use multiple filters, you make this more steep and more steep. That's what's happening in that example, because in that example, your unmodeled dynamics are on this region. If you use standard adaptation, it can excite them. But with decreasing this slope, it provides better adaptation other than lag, because I am not using that filter in the control, but I am using only in the weight update to shape its frequency. Does this answer your question?
Yes.
Thank you very much. Yes.
When you do your Lyapunov proof, the results actually support the observation that more filters improve the performance?
In the Lyapunov, so basically, in the Lyapunov analysis, the additionally introduced terms cancel each other. Basically, you have only V dot equals to minus E transpose RE. And Lyapunov analysis only shows that error goes to 0. But this cost function, eventually, you would like to drive this to that filtered version. And if your filter behaves like this, then basically at high gain, at high frequency content of the weight update load, you can think like it is like a sigma modification term, right? If it is high frequency, this weight update load does this. But if it is low frequency, it drives it to this region. Basically, you can achieve still the same property of the adaptive control load, but on the low frequency content. And the rest, it acts like sigma modification. Any other questions?